on this computer. And two things happened, I guess, yesterday in the pre-lecture video and in today's lesson. Not really any new material per se, but we've added two new situations to rotational motion. Okay, and I'm going to share with you my PowerPoint, and then we'll go on to questions. But I just want to make sure you didn't miss the point. And so hopefully you're seeing, yep, I see the green border. This is one of the problems I did. I did two fairly challenging problems in the pre-lecture video having to do with Newton's second law and the rotational analog to Newton's second law, that torque is equal to the moment of inertia times the angular acceleration. And the significance, I guess, is had I given you problem two here, 2 weeks ago, 2.5 weeks ago, the tension on either side of that pulley wheel at the top would have been the same. But now we're giving the pulley wheel mass. Maybe it's a disk, has moment of inertia. Then you can look up the moment of inertia for a disk on a table. It happens to be 1/2 the mass times the radius squared. And now because the pulley wheel has mass, as the heavier mass drops and the lighter mass goes up, which I'm hoping is what your instinct would tell you, the tension on either side of that pulley wheel is no longer the same. And so you have to designate it with two separate symbols. And it seems to me that if the mass is pulling downward, mass 2 is pulling downward over on the right side, that means the tension on that side must be greater than the tension on the other side. You need a greater torque making it rotate clockwise, the pulley wheel clockwise, than you do counterclockwise. Okay, and so that's a subtle point when you're reading problems like on the midterm exam, which I just want to warn everybody. I think I warned one of my lab sections. The next midterm exam is 2 weeks from today. A lot more time. We're going to be talking about other subjects. You have to know the Newton's second law problems, pulleys, masses, inclined planes, maybe. There's going to be a problem like that. And truthfully, you can't learn them all. So if your goal is to try to memorize problems, that isn't the way this works. There's creativity of people who've written physics books over the years. There's just a million problems. You can't know them all, but you have to know the fundamentals on how to solve them. And hopefully that's what I demonstrated in last night's video. I'm going to do a problem here today for that. But that's an important thing. But where I was going with that is, if you have a problem like this, make sure you understand what type of pulley it is. If it says something like a massless pulley, well, then it has no moment of inertia, okay? And then the tension on either side of it is the same. In a case where we give you the mass of the pulley, well, that would mean that the tension on either side of the pulley is not the same. And that adds perhaps another unknown to the problem for you. Okay, any questions on that? So just a new wrinkle. I mean, we could have done a problem like this without a massive pulley, without a pulley with moment of inertia 4 weeks ago, but we made it a little more challenging now by giving the pulley mass, which in real life it would have. And that is sort of what physics is about. You know, we take away friction, we take away mass from pulleys. The string that connects those masses has no mass of its own. It's just this. We talk about massless strings. As you move forward in physics and take more advanced classes, even we get rid of some of those assumptions, and we try to make the problem more real life. The model becomes closer to real life, and this is just the first example of that. All right, the other thing we talked about was rolling motion. Okay, again, it's just rotational motion, just a rigid body rotating, just like the pulley wheel was rotating. Here we've got the bicycle wheel rotating. I put a little red box with my drawing tool around the diagram I want to focus on because it makes a big physics point, I think. Early in the semester, I think I made the argument that when we talk about motion, there's really three types. There's motion along a line. I call that translational motion. And in the box diagram down there that I drew, the first one says translation. And you could kind of think about, what if you just had that wheel being pulled but not allowed to rotate? Okay, maybe there was no friction at the interface between the wheel and the ground, and so you just pull on the thing and it never rotates. Well, it would have translational motion. Okay, so last night we added on rotational motion, and you can see that means the top is rotating there's a velocity at the top, which is to the right because it's rotating clockwise. At the bottom, it's rotating clockwise. The wheel's rotating clockwise. So there's a velocity to the left. And those two combine. Okay, so three types of motion: translational motion. The middle figure of this diagram shows rotational motion. There's a third type that I mentioned, oscillatory motion, springs that oscillate back and forth. Unfortunately, we're not going to be able to do a whole lot with that because it does require calculus to solve, and so it's an algebra-based course. So that type of motion isn't going to get much of a look this semester, but it is out there. Okay. In any event, what you can always do is add these types of motions. They're independent of each other, but you might have to add them in a situation like a rolling object. And so what you can see is the author of our textbook who drew this diagram says, hey, take the translational motion, because it is translating. Even when the wheel rotates, it translates. Take the pure rotational motion that we've been talking about, okay, and add the two. And one of the things you notice is required then is at the point where the wheel hits the ground, the speed instantaneously has to be zero at that point, okay? And then at the very top, notice that the two velocities are in the same direction, okay, in the two types of motion. And so you have double the speed up at the top. The axle, the dot there, it moves at the what we call the center of mass speed, okay, the center of gravity speed, if you want, the speed at which the wheel is actually moving. And so a rolling object, do understand that all points on the rigid object aren't moving at the same speed anymore, like if it was stationary, like the object in the middle, okay, where they're all moving at the same speed. All points on the object are moving at the same speed. The edge of the object are moving at the same speed, but just in different directions. Okay, and the good news though is the equation that we know of for rotational motion, the relationship between the angular velocity of the wheel, omega, and the translational velocity of the center of gravity point, they are still related by the velocity is equal to the radius of the wheel times the angular velocity. So it hasn't changed. It's just kind of a subtle difference when something is both translating and rotating, as opposed to just rotating around a stationary center of mass. Okay, any questions on that or any of the problems I did last night in the pre-lecture video? All right, like I said, I'm going to do one more here in a second. It's a fun one that I think is worth taking a look at. But I got two questions for you if nobody's got questions. And let's start the poll up. Let's see, that's the problem I did. There's the first problem. And you can read that while I open up the poll. And launch it. And what we're comparing here is, okay, you're not letting me move that. Are we locked up? Nope, that can move. There, now I can move it. Just have to move my toolbars out of the way. What we're comparing here is how far the wheel has rolled, I guess is what we're talking, rolling motion, as compared to that green arc length there between points P and P prime. And we're saying that the axle moves 4 meters. What's the length of that arc right there between P and P prime? Yeah, a couple of people jumped in right and said, well, it's obvious. And it is to some people. And trust me, I've been doing this long enough. It's not obvious to everybody. But yeah. And some of you, I think, are just messing with me in the morning, purposely picking wrong answers. I don't know. You never really know. All right. I got 19 of 26. We're missing 3 people here today, apparently. And we're over a minute and a half. This one's too straightforward, I think. And immediately 3 or 4 people jumped in, probably like, it's too easy. It's got to be 4 meters. And you're exactly right. But not everybody, didn't almost muted myself there. Not everybody recognizes that. I got something in chat. Yeah, if the phone's not letting you submit, appreciate that. That lets me know not to wait for everybody to come in. All right, so in any event, yeah, 4 meters. That green arc has to be, come on, toolbars. Zoom's not cooperating here this morning. puts toolbars on top of toolbars for me, so I can't see things. And pop-ups on top of it. That green arc, even though it might not look like it's 4 meters long, if that point right there, P, is the same as that point right there, as the wheel rotated, this arc right here used to, each point on that arc used to be along the ground somewhere. And as the wheel rotates, absolutely 4 meters is the right answer. Okay. And that is why the velocity is equal to the circumference over the period, which is omega times the radius. Okay, circumference being 2 pi r divided by the period. 2 pi divided by the period is omega for rolling motion. So the equation that we've used for just rotation of a stationary object still works. And this is the reason, because those two distances are the same. Stop sharing it. I got one more to do. And let's move on to the next problem while you're reading that. Comparing torques, two that are the same, but the moment of inertia of two objects are different. So let's draw two objects that might have different moment of inertia. There's A, there's B. This is supposed to be round objects, by the way. All right, the majority are getting it. Some people are seeing it backwards. So I guess that's good. The majority have it, but a significant number have it exactly backwards. Sometimes exactly backwards is okay if you can just correct that as soon as you see it and you don't make the same mistake next time. Yeah, we're pretty even between correct and backwards. All right, I'm going to stop here. We got a majority in, a quorum is voted. And here is, I'll share the results with you. And you can see half the people have it right and half the people have it backwards. We're between B and D here. That's good. And hopefully you can see why the moment of inertia of this one, assume they have the same mass even, but for a cylinder, for example, the moment of inertia is 1/2 m times the radius squared. And so this one, A, clearly has a smaller radius than B. And so greater moment of inertia for B, smaller moment of inertia for A. And so if you're a mathematically oriented person, you might write something like the moment of inertia of B here is greater than the moment of inertia of A, right? Okay, and so let's talk about angular accelerations then. An angular, that's supposed to be an alpha, just a lousy looking alpha. That looks a little better, kind of like a fish, but the line goes upwards, almost like an infinity symbol where it's chopped off. Any event, that is equal to torque divided by moment of inertia. Okay, and that should remind you of linear acceleration, which is a force divided by a mass. Mass is a unit, a quantity that represents resistance to translational motion. Moment of inertia is a quantity that represents resistance to rotational motion under the influence.
Kolsky,
What's that?
I have a question.
Sure.
So you wrote that the inertia of B is greater than A,
Yeah.
but in the problem it says that the inertia of A is.
Oh, okay. So thank you. Yeah, I would have gotten it backwards then too. And maybe that's why some people got it wrong. So this should be B is what you're saying. And this should be A, right? Yeah.
Okay.
And this should be B, and that should be A. Let me clean that up a little bit. Is that your point?
Yeah.
Yeah, you're absolutely right. I was off doing my own problem rather than the one that was asked here. Okay, so let's make sure we got these right. Yeah, it does say A is double B. And so A is right here. So the moment of inertia of A is double B, B. Thank you. Who is that? Who just piped up with that?
Emma MacTurk.
Emma, thank you. You get a point today for catching me being silly. All right, good. So we got that. A is bigger than B by a factor of 2, obviously. And so let's see, we say the same torque. So if we look at the angular acceleration of this one, and let's relabel them, the moment of inertia is twice as big. So the angular acceleration here would be equal to the same torque divided by twice the moment of inertia. Over here for B, so that's A, right? The moment of inertia of B is half. And so the angular acceleration here will just be equal to the torque. And I guess I'm saying I'll make this IB, and A is double that, B. And so you can see, because I'm dividing through by a 2 here, well, that makes D the right answer, doesn't it? In the ratio of angular acceleration of A to B, okay, there's that extra factor of 1/2 in A's in A's angular acceleration, because the moment of inertia is doubled. Remember, it's an inverse relationship. And I probably could have just said, hey, it's an inverse relationship. If I double this, that means this goes down by 1/2. And if that's a quicker way to the logic, then forget all the chicken scratches here. But I think it is all you have to see that. You have to see that moment of inertia and angular acceleration are inversely related. Okay. So those of you who chose D, you got it. For B, you had it backwards. You had them directly proportional, and they're not. They're inversely proportional. Questions on that? And thank you, Emma, for keeping me from being silly here on a Friday morning. I'm going to stop sharing this, and I'm going to show you the worksheet for today. And I'm going to do one problem, and then you're all going to do a second problem. So I can stop sharing that and put that away. And instead, I'm going to go with my iPad. One of these days, I have to buy myself a new one. This guy is a little bit old, and my cool stylus that I bought this semester. Screen mirroring. Where does it? All right. And this is the problem I'm going to do, which I think I could have given it to you again a couple weeks ago. I think I did an inclined plane problem, except it was a kind of a rectangular shaped object on the inclined plane. Yeah, we did skiers going down inclined planes. Okay, but this time the object is going to go down the inclined plane, and it's of course going to rotate down the inclined plane, right? It's going to spin as it moves downward. So it's going to roll. That's why we've been talking about rolling motion. And I think this problem is either gotten correct or gotten incorrect very early on when you draw the free body diagram. Okay, so let me do that first. And if you're finding yourself, when you encounter a physics problem like this, not drawing a free body diagram, well, then I've failed miserably. And that's just the way it is. Okay, so I'm just going to draw my inclined plane. I don't need the whole thing, but I want enough of it to get all the forces visible. There's I just called it a round object. It could be a ball, it could be a cylinder, anything that will roll down the inclined plane. In fact, I'm going to compare those two at the end, because the very first thing I want to do is find the acceleration of this ball down the inclined plane. We'll compare it real quickly to what if it was just a box sliding down the inclined plane, which has a greater acceleration. And then I want to know how long it takes to get to the bottom, assuming that this distance right here, I think we call that D in the problem statement. Okay. And you can see the angle theta is given right there. And then if I compare a spherical object to a cylindrical object, a ball to just like a soup can or something, who's going to win getting down to the bottom? And we can do this. You notice one thing about the problem statement that I think bothers some people still, but hopefully it doesn't. There's no numbers in this problem. So my final answer is going to be just a relationship, an equation. Okay. But it's not a fundamental equation. It only applies to this particular example of a ball or a cylinder rolling down an inclined plane. Anyway, enough on that. Let's get the forces in place here. And hopefully at this point in the course, you look at this immediately and you go, well, everything we got has a force of gravity, which we call weight. And here at the surface of the earth, m times g, right? Now, okay, if you look, I actually don't want to use that symbol. The symbols I'm using in this problem, and I should be true to them, capital M, moment of inertia of that thing, it has some radius r. Okay, so it's capital M, capital I, and R are my symbols that I should be using. So I'm going to just make a little modification here. I'm going to write weight is capital M times G, because those are the symbols given in a problem statement. And as a solver of the problem, you're kind of obligated to stay with the symbols you're given. Okay, that's the obvious one. I hope nothing's changed from earlier in the semester. I hope everybody can see that that inclined plane puts a normal force right there. Okay, and one of the points about rolling motion is if something is going to roll, there has to be a friction force. Those of you who grew up and learned to drive up in the northern part of the country, or at least a part of the country where it snows enough so that you have to drive in ice and snow, realize that if there is no friction between the wheels of your car and the road, your wheels just spin and you don't go anywhere. Friction is necessary for rolling motion of a tire or a wheel on an object. So there's a friction force. And normally we've told you to put forces like in that rectangular box 2, 3 weeks ago when we did a problem like this. We told you to put it right at the center of mass, which on Wednesday we talked about the center of gravity, right through the center of the object. Okay. But this time we're going to put it where it occurs, which is right at the interface of the tire and the wheel. So the wheel and the inclined plane. Okay, so right there, and it's a kind of a lousy looking angle I've drawn, but there you go. All right, now this suggests, like it often does on an inclined plane, that a good coordinate system might be that way. Okay, because the normal force is along the y direction, the friction force is along the x direction of that coordinate system, and ultimately this thing's going to accelerate down the inclined plane, so the acceleration is also along a principal axis of that coordinate system. The only force that's not along the x or the y axis of this coordinate system is, of course, the weight. And as always, our fix for that has to be to get the components of the weight along those principal directions. Okay, and so I look and I go, well, there's the x component of the weight, and there's the y component of the weight. Okay, and as soon as you draw the components, you really no longer need the weight, right? Because the x component plus the y component added together as vectors give me the weight. And so I no longer need that. The question, I guess, is what is the x component of weight and what is the y component of weight? Okay, and the x component of weight, you got to get where the angle theta is, and hopefully you realize the angle theta is right there. The x component is the side which could be drawn right there opposite that angle. The trig function that's associated with sides opposite an angle is sine. So that would be the weight, m times g, times the sine of theta. And of course, if the x component is sine, the y component is just the other trig function, the cosine. And once you get one right, you should get the other, or you get them both wrong. That's just the way it works. Now, hopefully nothing new here, but for the umpteenth time, okay, getting components of a vector on an inclined plane comes home to roost here. And so you got to be able to do it. All right, so now we have two types of motion here, we said. I went through the trouble of finding the y component of the weight, but it really isn't significant other than I think if you look, the normal force and the y component of weight, they seem to have to add to zero because as long as this object just rolls down smoothly, it doesn't bounce up and down. There is no motion in the y direction. And so the sum of the forces in the y direction have to be zero. So that tells me normal force is equal to the weight. But that's not a attribute being asked for here. But I think that has to be true, so that if you subtract normal force minus the y component of weight, you get 0. Irrelevant, but true. But what we do care about is the x component of the weight and the forces that lie along the x direction. Even though they're not tied to the center of the ball or the cylinder here, I have in the x direction the sum of the forces, the net force, if you don't like writing that Greek symbol, if that weirds you out a little bit, but the net force is the x component of weight to the right and the friction force to the left. And they're not balanced because this thing is moving. So that has to be equal to the mass times the acceleration, right? And so that's a fundamental physics law. We're starting with first principles here. We've drawn a free body diagram. We've done manipulations on forces to get components. And now the first big equation from physics is that the x component of weight minus the friction force is equal to the mass times acceleration. And I could even simplify that a little bit. M times g times what we said here, the sine of the angle theta minus the friction force is equal to the mass times acceleration. I always stop at this point to make a consistency check. Are the forces and accelerations that are in the same direction, do they have the same sign? And remember, the only way you can be consistent is if your forces are on the left side and mass times acceleration is the right side, because Newton's second law says the sum of the forces is equal to mass times acceleration. Then now you have to be consistent. Weight is down the inclined plane to the right. I made it positive, the x component of weight. The acceleration is in the same direction. It's positive. The friction is in the opposite direction. That's why it's negative. And so my consistency check is good. By the way, you can flip all those signs. You could have minus, plus, minus, and you'd be every bit as right because mathematically that would just represent multiplying by -1. All right, so let's get rid of those. And look at that, too much erasing. Don't have the fidelity that I would want. Is equal to, and then is equal to, put those back. All right, so we're good on that equation. The problem here, of course, is we don't know what the friction force is, and we don't know what the acceleration is, do we? Two unknowns. Everything else is given in the problem statement, the mass, the angle, well, the acceleration due to the acceleration due to gravity here at the surface of the Earth. That's just a constant we know. But the bottom line with that equation is there's two things we don't know, and so we can't solve for acceleration directly from that because friction, if you notice in the problem statement, is not given to you. Nobody says, hey, that you have a known friction force of X, 5 newtons. Don't have that. Okay. So we have to come up with another relationship here that would allow us to maybe solve for the friction force. And of course, what I'm going to do there, and I'll change colors here just to note we're moving to something different. We'll go to this ugly green that we get here. And that is that the sum of the torques are equal to the moment of inertia times the angular acceleration. And I write that one out as opposed to what I did with sum of the forces equal to mass times acceleration, where I just did it. Okay. And I suppose if you look at the three forces that are acting on this object, the normal force, even if you decide the normal force is right there, is going right through the center of rotation of the object. The weight force comes right out of the center of the object. Because of that, remembering that torque is equal to R times F times the sine of theta. For both of those two forces, R here is 0. So they give you no torque. But the friction force is acting at the interface between the wheel and the road. And so it does have a radius. And in fact, the problem statement refers to that radius as that thing I kind of circled, capital R, because capital R is right there, any radius. So there is only one force of the three that can exert a torque, and it's the friction force. And so it's the only one. So it's R times the friction force, sine of the angle. What's the angle between the friction force and the radius? Boy, it sure looks perpendicular to me. Right here, perpendicular. Okay. Why didn't it draw? Right there is a right angle. So sine of a right angle, sine of 90 degrees, hopefully you know is 1. So I don't have to write anything right there. And that's got to be equal to the moment of inertia times the angular acceleration. Now, there was a relationship that we discussed when we first started talking about rotational motion between that and that. Okay. In fact, we said that translational accelerations are equal to r, the radius, times the angular acceleration. We also said that velocity was equal to r times angular velocity, but the one we're going to use is that one. Okay. And so that means that r times f, the torque that the friction force is putting on this round object, is equal to the moment of inertia times solve for alpha here, the angular acceleration, the translational acceleration over the radius. And I can go even one step further. I can bring the r over to the other side of the equation and solve for the friction force. That's supposed to be a capital R, poorly written here. And so now I have that result. What do you think I'm going to do with it? Well, I think you hopefully realize the reason I've changed colors here is so that I can now combine those two results. Okay, from the two fundamental equations of physics, I can put that guy right in there and rewrite the equations. Because again, I've got another equation that came from the sum of the torques being equal to moment of inertia times angular acceleration, what I've been calling Newton's second law for rotation. Okay, but same two unknowns. I don't know the acceleration. I don't know the friction force. Remember, moment of inertia was given, or something I could look up. Radius was given. So I've got an equation with the same two unknowns. Bottom line, an algebra expert would tell you have two equations, two unknowns, time to solve for it. This one's just begging for me to plug friction force into the blue equation. So let's do that. I'll change colors a third time just to be obnoxious here. And so that means that m times g times the sine of theta, let's see, minus I times the acceleration over r squared has to be equal to the mass times the acceleration. Okay. And that was accomplished just by making that substitution right there. Okay. And now we've got one equation. And if you look, the only unknown in it is acceleration. And so a little bit of algebra to solve for it, right? And that's hopefully what we do. So I'll bring that guy to the other side of the equation. M times G times the sine of theta. Looks like it's equal to mass times acceleration, plus, when I bring it over to the other side of the equation, moment of inertia over r squared times acceleration. And in order to solve for acceleration, I'm going to have to factor it out. And so it's mass plus moment of inertia over r squared. Now, just a check I do when I do problems like this thing in brackets has to have units of kilograms, doesn't it? Mass has units of kilograms. The one that might be a little more of a question is what's the moment of inertia divided by radius squared? What are the units there? Remember that the units of moment of inertia are kilogram meters squared. So sure enough, if I take a moment of inertia and divide it by a radius squared, that would be divided by a meter squared. The second term here also has units of kilograms. And so I didn't make an algebra mistake. I didn't forget one of the R's somewhere along the way. And so that's just a check. You hear me harp on units. It's one that tells you, hey, did you make an algebra mistake getting up to this point? Because it's easy to do. We all make them. All right. So in any event, now it's time to solve for the acceleration. And I'm going to use those two terms. So it looks like m times g times the sine of theta, the inclined plane angle, divided by the mass of the thing, plus the moment of inertia divided by the radius squared. And that is the answer for the acceleration. Now, let's try to figure out now how long it's going to take in order to get to the bottom of an incline. Okay. And I'm going to just ignore this problem because I know I got white space for it. This is the one for you. Not quite as hard as the one I'm doing, but I'm just going to use the space. We'll bring down that acceleration that I just did, just so we don't forget what algebra I did up above. M times G times the sine of theta divided by the total mass again, plus the moment of inertia divided by the radius squared. And we want to know, well, how long does it take to get to the bottom? Is physics cumulative? Well, yeah, it is. Okay. So that means I'm going to use this equation. That's a constant. Everything in there is a constant. There's no time or position that the acceleration is a function of. That's a constant. So all those constant acceleration equations from week 2, they're here. Okay. So I could go x final is equal to x initial plus the initial velocity times the time interval plus 1/2 the acceleration times the time interval squared. Okay, now the problem implied that this thing starts from rest. And I think I can choose to put the origin right where the ball starts or what the round object starts right at the very beginning. So that kind of makes my life a little easier. Remember, the final position we said was going to be a distance d down the inclined plane, right? I called it in red there, I called it d. So that's, if it starts at 0, the final position is going to be d. D maybe for displacement if you like. And so I put that on in. D is equal to 1/2 that lousy acceleration equation, mg sine of theta divided by the mass plus the moment of inertia times the radius squared times the time interval that I'm looking for squared. Okay, we're rolling here. Hopefully I'm boring you with algebra. If I want to solve for the time interval, I guess I need to go 2, when I get my pin back, 2 times d times m plus the moment of inertia over r squared. I just brought these two guys to the other side of the equation. And then I got to divide through by mg sine of theta. And that's going to be equal to the time interval squared. That's a lousy looking theta there. That looks a little better for theta. If I want to get the time interval, well, I just take the square root of that. Okay, and hopefully that's what I got written on my paper. Yes, I do. All right, now I said, what if we were to do a race? What if we were to do a race between a sphere and a cylinder coming down the inclined plane? And if you look up the moment of inertia of a sphere, you'll find the moment of inertia is 2/5. That's supposed to be a 5. I know, write 2 over 2. 2/5 mr squared. And the moment of inertia of the cylinder, look it up on a table, 1/2 mr squared. And so that's going to go in right here. And we'll see how it simplifies. Okay, so let's solve for the time interval to get to the bottom of the inclined plane. In the case, I did cylinder first, so we'll do cylinder first here. And I look and I go, let's see, 2 times d m plus 1/2 mr squared divided by r squared. All that over m times g times the sine of theta. Again, fixed angle, all that. Look what happens here. R squareds cancel. And in the numerator, I now have, let's see, m plus 1/2 m. That's 3/2 m. So I've got 2 times d times 3/2 m, all that over mg sine of theta. It sure looks like the m's cancel, doesn't it? Sure looks like the 2's cancel. And I'm left with 3 times d times nothing. That m canceled, so I'm done. And that's divided by g times the sine of theta. Now, I don't know about you all, but I find that to be a very surprising result. Okay, I find it to be surprising. Wouldn't you have expected that the time it takes to get to the bottom of the inclined plane depended on what the mass of the object was, what the radius of the object was? I would have expected that. I'm amazingly surprised right now that in the previous step, those two things canceled. The only thing that matters is what the angle is. Any object I allow to roll down the same length d at the same angle will have the same time interval to get to the bottom, as long as it's a cylinder in this case. Any cylindrical object, I suppose I should say. Because the next thing I'm going to do, of course, is compare to the time interval for a sphere. We'll go sphere, pH. Same equation, okay? 2 times d times m. This time it's 2/5 mr r squared divided by r squared, all that over mg sine of theta, okay? And the r squareds once again cancel. And I've got 1 plus 2/5. I got to get a common denominator here. That's 5/5 plus 2/5. That's 7/5. I can do that. I can do that. So it's 2 times d times 7/5, again, 1 plus 2/5, times m, all that divided by m times g times the sine of theta. M's cancel. And I guess I'm left with 2 times 7. That's 14 over 5 times d over g sine of theta. Exactly the same thing. The time it takes to get to the bottom is only dependent on the angle and how far to the bottom. And the only question is who's going to win here? Which is bigger, 3 or 14/5? Well, I think the answer is 3 is a bigger number than 14/5, right? 15/5 would be 3. So the time interval for the sphere, I guess, is just a little bit shorter, right? And so it will have a slightly smaller time interval to get to the bottom of the inclined plane. It's going to win. All right. That's what I got for you. You've got about 8 minutes or so. Any questions on that problem? All right. Well, you got your choice here. It's a Friday. So I'm going to say for this next problem, which I looked at, it's actually a little bit easier, but you can either spend the next 8 minutes working on it, and I'll be here to help you with it. I'm not going to go into breakout groups. That just takes time. Or you can do it over the weekend. But the bottom line is that other problem that's on this one is due on Monday. And I would urge you to just look the same thing, do it the same way. You've got 2 objects in that problem. You got to write a Newton's second law problem for the square object, the rectangular object, the box that's on the inclined plane, and you have to write a rotational Newton's second law for the pulley that has a string coming off of it that's attached to the box. And just like I did, you have to combine those 2 equations, figure out, I believe we're asking you for acceleration. Want tension, we want angular acceleration, we want torque, we want the moment of inertia, and we want the angular speed. So not linear acceleration. In your problem, instead, you're going to solve for angular acceleration. Okay. Any questions on what I did? Complicated problem. I'll tell you this, if this bothers you, this is probably as hard as it gets with the Newton's second law problems. The one I did today is a challenging problem. The 2 that I did in the video last night are challenging problems. They're not going to get any harder than that. So that's the good news. And I think the second problem that you all are going to do is actually not quite so hard. Any questions? All right, well, I'll be here. I'll stay around for office hours. Even though I don't normally have them on Friday, I have time today. Go ahead and go work on that. If you don't have time right now, you can work on it sometime later on, and turn it in Monday, though. And I appreciate a number of you did turn in the extra credit for today. Hopefully you saw it was just like the teeter-totter problem, and you were good with that. I'm going to stop the recording unless anybody has any questions. And I'll be here if you want to work on a problem. If you got to move off to your next class, that's fine too. Have a great weekend. Hope the rain goes away and you get some fun out this weekend too. Stopping the recording.